Good morning. Thanks for the introduction there. Just a disclosure, we received some research support from GE Healthcare in this polarized endeavors. Okay, I want to leave this slide up here for a sec for a couple reasons. First, if you want to download my slides, follow along, make any notes on those. I posted those there at the top at my website. Fortunately, my name is unique enough that I can Google myself and it's not too hard to find. Go ahead and do that if you need. Then here's the outline of what I'm going to go through this morning. The first half I'm going to be talking about more of the physics behind, like what do you say when you mean hyperpolarization, and then some of the specific techniques there. I will go briefly through all of these, but with a little more emphasis on dissolution, dynamic, nuclear polarization. Because that's a little more the focus here, but I think it is important to be aware of that this is not the only method or game in town for doing hyperpolarization. And then I'll wrap up with going into imaging methods in terms of RF pulse strategies, acquisition strategies, and a little bit on analysis and what we call usually kinetic models for hyperpolarization. So I'll go through a little bit of, I won't spend too much time on this, but spin polarization, as most of us here are aware, in its absence of a magnetic field, we have randomly oriented spins, and in the presence of a magnetic field, we get some orientation, and the basis of all other types of MR not hyperpolarized is this small polarization fraction, a fraction of a percent, depending on our nucleus and field strength. And so all the rest of MRI is basically built on this small percentage. And this is where hyperpolarization comes into play, is actually trying to get more than that small fraction of spin alignment with or actually against the magnetic field. And with hyperpolarization methods, instead of being in the 0.0001% regime, where 4 or so orders of magnitude higher in terms of a lot of what the techniques can achieve, if polarizations greater than 50% are now being routinely reported for our dissolution DNP systems. And again, here's the 3 methods that I mentioned at the beginning: optical pumping, parahydrogen-induced methods, and dynamic nuclear polarization. So I'll get the other non-DNP approaches out there first. Just one slide here on spin exchange optical pumping. This is a way to polarize noble gases, mostly helium-3, and xenon-129 is now the preferred gas to polarize, and it relies on this application of a circularly polarized light intersecting with a mixture of a noble gas and these alkali metal vapors. You see there's some, I think, rubidium in there, if I remember correctly. And then the major application here, because we're dealing with gas, has been pulmonary imaging and for lung applications. Then a little bit more related to DNP is actually the parahydrogen-induced polarization methods. These rely just at a very high level, rely on the fact that parahydrogen, which is the singlet state here of hydrogen gas, and it's MR invisible, but it can store magnetization. And so all parahydrogen methods, which there's a number, I've shown an example here, SABRE, there's Pasadena, and some other acronyms in there, but they're all based on having parahydrogen and converting that polarization into some other nuclei. Just a more description here of the SABRE technique, which is really one of the emerging approaches and promising approaches for parahydrogen methods, is relying on some catalyst here. And depending on how you do it, you can increase the scope of what type of agents you can polarize and how efficient that is. Before we get into DSP, it's important the limitations of parahydrogen. The pros of parahydrogen are simple, fast, and easy. This is something that any lab could relatively easily set up with not a lot of money. The limitations and why that's not more of an emphasis in this talk is that the substrates you can polarize are less biomolecules, and we have this issue at the bottom here of need to remove this toxic catalyst prior to an in vivo sort of experiment. Okay, but now coming to what the technique that is becoming most widely used here is dynamic nuclear polarization. And the schematic here is that we take whatever compound we're interested in polarizing, so something, say, enriched with carbon-13, this can also be nitrogen. We dope this with some source of free electrons, also called free radicals or electron paramagnetic agents. And then the idea here is that you put this sample in a magnetic field and actually drop the temperature. And at this point, you reach this area here where we actually have almost full electron polarization. And then the whole idea of DNP is actually transferring this full polarization from the electrons to our nuclei, whatever they might be. And you actually get even a little bit of increase of polarization here of your carbon just by going to low temperature as well. And when you see the next slide, let's see. Can you check advancing to the next slide? Or are you able to do it? Yeah, so here's an example of the preclinical polarizer that's out there, the HyperSense. It's under these conditions of high magnetic field and low temperature. And again, we have a very specific microwave frequency that drives the polarization transition from the electrons to, in this case, carbon-13 nuclei. Let's see how this goes. So the other part of DNP is dissolution, and that's what this is going to illustrate. So we take actually a buffer or liquid, we superheat it, and this is merge, somehow deliver this superheated liquid into, now in here is where we'd have our polarized sample that's frozen under a magnetic field here, and then we're going to quickly dissolve this frozen sample into the liquid state. And the innovation, this is the innovation that is really driven the whole field, is that we get this liquid sample out, it's injectable, it's maintained the polarization from this frozen state. And that's a diagram is from an older system. This is the modern clinical use system where you can polarize 4 samples, do quality control, a little higher field and lower temperature, boosting polarization as well. Finally, one of the advantages of dissolution DNP is we actually have a large number of biologically relevant and biologically compatible agents we can polarize, so a lot of metabolites you see over here. And this is the reason why this is a successful and growing field, is this here. And I'll refer you to this review, is relatively recent, although some more information there. So if we're going to consider now, we've done dissolution DNP, or one of these other polarization methods for that matter, we still have the Bloch equation. This is still spin physics. So actually nothing has changed here. You should be comforted, I hope, by that. But you do need to think about things a little bit differently. And that's because of the T1 term in the Bloch equation is a return to equilibrium, and the usual way we think about that is T1 recovery back to M0, but in this case we've highly perturbed ourselves above M0, so we, in hyperpolarized MRI, we have a T1 decay instead of a T1 recovery. And so this becomes a key parameter for our experiments. What's the T1 of our molecules that we're polarizing? Try to make that as long as possible, and you can see it's actually reasonable for doing in vivo experiments with, for example, C1 pyruvate. Then the other thing we want to consider in an experiment where we're using hyperpolarized magnetization is that any sort of RF excitation here is deflecting as usual, deflecting the net magnetization. Right, and then T2 decay is basically eating at, so we're going to get T1 loss of this polarization, and any RF excitation is going to start taking away from our total magnetization we have available. And just to set the stage for now some of the other imaging techniques that are talked about, this is what a typical spectrum is going to look like from a hyperpolarized C1 pyruvate experiment, where we're going to have easily up to 5 or even 6 resonant frequencies present due to the metabolic conversion of pyruvate to these other compounds, lactate being the primary one of interest for cancer, but also alanine, bicarbonate, and in some cases carbon dioxide even as well can relatively easily be detected, and also the hydrate form of pyruvate as well. So we have to deal with this spectral component in any experiment. Now the whole imaging procedure I'm going to outline here is we have some hyperpolarization step. This does take an hour or 2 to complete. And then once we've dissolved this sample, now we're fighting this T1 decay that I mentioned before. So maybe we have a minute of T1 decay, optimistically. So the experiment goes fast. So we rapidly dissolve, we get everything ready, we actually run the sample into the magnet, inject it into our subject, human or animal, and we image very quickly. This is an old example here from my prostate tumor mouse. So this would be typically what we might see. You see pyruvate being the injected substrate, distributing throughout the body, and then the appearance of alanine and high lactate in this case within the tumor. So I'm going to go through divide up an MR pulse sequence into very simple components, right? We just have our RF excitation, if you could almost see it there, and some sort of readout where we need to do, in this case, spectral and or spatial encoding to do the experiment. And then we're going to repeat the usual view as we have T2 decay, T1 recovery, and this sort of repetition. Our experiment, we have T2 decay and T1 decay. So as far as RF pulses go, we have 2 key considerations. We want to efficiently use this limited pool of hyperpolarization, and we also need to think about spectrally what we're doing. Are we exciting all metabolites or some? And one of the tools that we're using a lot of is spectral-spatial pulses. So this is a nice sort of example illustrating what happens with RF excitation. If we take just what you might do in a conventional imaging experiment, do a constant flip angle, read out the signal, and continue this on, is you get this actually signal that decays and becomes smaller and smaller, not decays, but becomes smaller and smaller because we're depleting the pool of magnetization here. So one trick that we use is these sort of variable or progressive flip angles that have been around for a while. And this is where we're going to dynamically update the flip angles here, usually progressively increasing, and often you want to use, by the end of your experiment, you're thinking, okay, I'm going to use the entire net magnetization I have available, so do a full sort of 90-degree flip angle at the end, and there's some nice, clever mathematics you can put behind this to choose these. The other trick that has become effective for metabolic imaging is what I call multiband excitation. So we're usually in a case where we have actually a large amount of polarization or signal from our substrate, say pyruvate, and the lactate detection or the lactate SNR is our limiting factor here. And if we do just our constant flip angle that's the same across everything, we might get this type of signal. The idea behind a multiband excitation is we say, well, we've got plenty of pyruvate to go around. Let's just tip it with a small flip angle. This is going to reduce the pyruvate signal, but we still have sort of sufficient pyruvate SNR. And then because we preserved the pyruvate magnetization, more of that magnetization can be converted to lactate and detected once it becomes lactate. So this gives us more lactate signal and for more time. So, and you can actually even combine these ideas. Won't go into much more detail than that and refer you to some references if you're more interested to see these concepts, but it's just basically a combination of the 2 things that I just described Now the other consideration is spectral selectivity. How do we deal with the spectrum? And this is about the level. I'm going to cover this here, but I want you to be aware that this is a tool that we use a lot as a spectral-spatial RF excitation, where we're doing some controlled excitation in the spectral regime as well as spatially. So we can do this for in vivo, either slice selective, slab selective type experiments. And if you're interested in designing some of these pulses and using some of these tools, we have a toolbox available to do a lot of that work. Okay, so that's that's what I'm going to say about for the RF side. Now I want to go into what we're going to do in the hyperpolarized acquisition space. And really, in my opinion, it's all about speed. The decay is fast. The metabolic conversion is also fast. It needs to be actually for this experiment to work in the short during the T1 decay time. So this is sort of a simple experiment, but if we go to the case where we do a large number of excitations to acquire an image, we're potentially going to lose signal to noise because of decay over that time that it takes us to acquire an image. So really fast data acquisition is important. We want to capture this information quickly, both for SNR as well as to capture it before it decays or capture it before it becomes something else. So I group our acquisition strategies into these three groups, basically from the slowest, typically slowest, to the typically fastest. We have MR spectroscopic imaging techniques, model-based techniques like Dixon. They're based on concepts of Dixon MRI or ideal, and then MRI with some sort of spectrally selective excitation, what we call metabolite-specific imaging. So going through that, we're also always going to, for the most part, in hyperpolarized MR, because we need speed, we're going to do some sort of accelerated MR spectroscopic imaging, like echoplanar spectroscopic imaging. We're now, instead of covering sort of one line in our spectral spatial K-space here at a time, as you might do with conventional phase encoding, we're going to cover some 2D space with like an echoplanar spectroscopic imaging. Or this is not the only way to cover the 2D space. Just like in imaging, you have a number of different trajectories. So this would be analogous to EPI, spirals, and maybe a rings type trajectory. We can do the same thing to accelerate MR spectroscopic imaging. And all of these are very powerful for our hyperpolarized experiments because we have this need for speed. And there's sort of trade-offs between these different approaches here. But what a lot of we're also moving towards is away from spectroscopic imaging and to other techniques. One of those that's nice and a little bit faster is we do something where we assume we have known chemical shifts here. So this is totally analogous to fat water imaging, where you're going to acquire data at different echo times, where you have different relative phases between compounds with different frequencies. And you can separate out the different components. And so we take advantage of, since it's not as simple a problem usually as just fat water, might have multiple resonant frequencies, we're going to acquire a bunch of different echo times and separate the metabolites out there. And the most common approach in the field to date is something like I call a spiral CSI, ideal spiral CSI. You're going to take use a spiral readout, but shifted at different echo times. And this step is basically your ideal separation into different images of different frequencies corresponding to pyruvate, lactate, pyruvate hydrate, and alanine in this case here. And there are also ways you can sort of take advantage of that even within a single shot technique if you have the gradient strength to do that as well. But really where a lot of the in vivo imaging is going is to what is called metabolite-specific imaging. And the idea here is we use a spectral-spatial excitation. We use that to only have a So what this plot here is showing, you can see the flip angle as both a function of frequency and position, so selective in both ways. And the nice thing about, particularly about C1 pyruvate, is the resulting spectrum is quite sparse. So we can manage this spectrum with a spectral-spatial pulse and only excite, say, bicarbonate with one excitation. You can shift the frequency, only excite lactate. You can shift the frequency again, only excite pyruvate. And this greatly simplifies the imaging problem. Now we just have one resonant frequency, so we can, do almost whatever we want with usual fast imaging techniques from other MRI, like a single shot or spiral in this case, or EPI I'll show as well. And this is really, the advantage here is this is very fast. You excite only one thing, you image it very quickly. But there are the limitations. You need to have this type of sparse spectrum, and you need to hit these resonant frequencies well. But this is being applied very successfully now in clinical studies. Here's an example you can come check out later this morning in the prostate, doing multi-slice prostate imaging, this in case with a symmetric EPI readout, but then 16 fully sampled slices within 2 seconds. This is quite efficient. And a couple other nice examples recently published, data in the human heart with a spiral readout where spirals become very important in cardiac applications where there's a lot of motion. And also some EPI applied in the brain. Again, stick around this morning and you can see some more about this approach as well. And just to do a brief comparison across these different types of techniques, again, they're generally, not always, but generally going from slowest down to the fastest there. The way that I see it is really the spectroscopic imaging is going to be very important for this flexible spectral content piece here. If we have a way, if we're not doing C1 pyruvate, but maybe other metabolites, other compounds where you have a more complex spectrum. And this is going to be a nice technique, but it does take a little bit more time. The spectral decomposition is kind of almost spectroscopic imaging, but making some assumptions about the peak locations. And then finally, this nice technique that works very well for what is being translated into the clinic, which is C1 right now, which is C1 pyruvate. It works great for that, so it's giving us the fastest speed we can ask for in terms of acquisitions. Okay, and to wrap up here, I'm just going to speak a little bit on now what we've done this acquisition. What do we do with this data? And there are numerous options as to how we're going to deal with this data. One of the most common is to set up some sort of kinetic model. And this is assuming that we're injecting pyruvate here. It's going to be converted to lactate. And then we're going to account for factors like the flip angles we've applied to pyruvate and lactate, as well as the relaxation rates. And this is shown here as well. This is an assumption we often make that it's a unidirectional model. So there's only conversion from pyruvate to lactate, not the reverse. And there's some nice work showing that this is generally true. Other ways you can look at this are lactate to pyruvate, or take the area under the curve, which is illustrated down here, of a dynamic time series from pyruvate and lactate. This is a personal preference, but I like this type of model here, just because there's nice work showing you can neglect the back reaction. We get a nice value that is semi-quantitative. And we can incorporate any effects of our sampling or bolus delivery strategy into that. And those couple recent. So in addition, this is a nice paper comparing some of these models, and this is another nice recent paper looking at how to choose a kinetic model, because it's not. We can make it more biologically accurate, probably. In this case, part C, where you'd have a vascular component within a voxel, an extravascular, extracellular, and then an intracellular compartment. And this is what I'd love to use in every experiment. Do we have the information always to capture all these compartments? And what this showed is, well, it's going from this type of model where you're lumping everything extra vascular together that you may not have the information to go go to this model in C. The other thing that we often need to do is make some assumptions about both the backwards conversion rate, or maybe the input, or our relaxation rates. So these are considerations to think about. Another approach that I've liked recently is what I call an inputless fitting, where you don't actually incorporate any information about the pyruvate input shape or bolus, and simply fit the change in lactate based on the pyruvate input at a given time. This is a nice simple model that's relatively insensitive, but we lose this nice estimate of perfusion, which it would be good to have in our experiments as sort of even if we're studying metabolism, this is potentially a for-free another measurement that we have of perfusion. And the last thing I'll show here and point you to is what I'm trying to develop for the community here is an open source toolbox where we have some, if you're starting in the field or you're established, you can come here, grab some tools. I hope I can convince some of you to contribute your own tools or your own code here as well. So you can have some resources for the community, for anybody doing these types of experiments to get into the field. And working on getting some more also data sets and phantoms in here that you could use as well to start getting into trying out things like the analysis. And thank you very much.